Let's get started. So today we'll continue look at more examples of the Christoffel symbol and geodesics. And hopefully today we will get to the transformation law of the Christoffel symbols and to see why it is not a tensor. That's the plan for today. So let's get started. So I'm just going to use this part of yesterday's notes. This is a quick summary of what we've done so far in the field of Riemannian geometry, although from a non-rigorous, mostly computational standpoint. So first of all, we imagine not imagine, but we consider or understand the notion of Riemannian space as a high-dimensional generalization of a surface in 3D. However, the notion of surfaces in high-dimensional Euclidean spaces in particular, is fairly restrictive. So we really wanted to consider the notion of a manifold, a Riemannian space, intrinsically. So we don't really care about the surrounding or the embedding Euclidean space, if that makes sense. So think about a sphere sitting in 3D space. Of course, the surrounding space is 3D, but we trying to imagine ourselves being creatures living on that sphere, like that's all we know. Right. So we would like to do geometry from the standpoint of inhabitants of that space, without taking a external observer's perspective. So to do that, we formalize the process as follows. We first impose a coordinate system on the Riemannian space. Of course, sometimes it's not possible to impose a coordinate system globally. But at least we hope, locally, you can always do that. Okay. In fact, rigorously speaking, Riemannian spaces is an example of a smooth manifold that could consist of that has a system of coordinate system, a collection of coordinate system called charts on it. So what we do here really is valid in a neighborhood sense. Okay. Locally, this is okay. And to do geometry, you don't only not only you need coordinate system, you also need something called a metric tensor. So the metric tensor is very similar to an inner product in linear algebra. So in linear algebra, a vector space on its own has only limited geometric meaning. So on a vector space on its own has only two structures, that is addition and scalar multiplication. For that, you can talk about parallelism. So if two vectors are scalar multiples, in scalar multiple, then they are considered parallel. However, you cannot generally, in a vector space, talk about the notion of length, the notion of angle, orthogonality, those kind of things. Metric tensor, inner product allows you to do that. With an inner product, you can define length, and you can define angle, you can define orthogonality, you can define projection. All those notions familiar in Euclidean geometry. So here, the notion of metric tensor plays a similar role. So it says that on the Riemannian space, infinitesimal length squared, which we call line element, is ds squared equals g alpha beta dx alpha d beta. In this equation, the summation convention is assumed. So here we have the line element, which is a defining computational, the primary computational tool, the fundamental computational tool in Riemannian geometry. And with the line element and metric tensor at our disposal, we can define the reciprocal metric tensor. So this is really just the inverse matrix of G alpha beta. Okay, and actually, I think it was in the stream on the 28th, we showed that G alpha beta really is a contravariant tensor. Remember, metric tensor on its own, the OG metric tensor is covariant with two lower indices. And the contravariant tensor, G alpha beta, it's actually indeed a tensor. You can show that, namely show G alpha beta satisfies the law of tensor transformation. Okay, so and then we define the arc length. So arc length is just the integral of ds. right? We have the line element ds squared, and ds is just the square root of that, so the integral would be, well, just the integral for that. So imagine if you have a curve on the Riemannian space written as xit, okay, xit t greater or equal to 0 less than t1. That's the parameterized curve on the Riemannian space, and you can write, okay, dx alpha. You can write dx alpha as x dot alpha dt, and dx beta as x dot beta dt, and you substitute that in and you integrate, you get this expression. So that's the arc length, and the geodesic is a curve that minimizes or extremizes arc length. Right? So extremization is perhaps more accurate because as we will see, it can also maximize arc length. Okay, and we're not going to get into the question of whether the extrema actually exists because this is very subtle and difficult to answer, but instead we're just going to assume such a curve exists and see what kind of condition it must satisfy. As it turns out, if we use the calculus of variation, namely the Euler-Lagrange equation, you can derive the geodesic equations. In this derivation, which was done on the 28th, near the end of the 28th stream, we have this nonlinear system of ordinary differential equation satisfied by the geodesic parameterization when the parameter is the arc length. So S is the arc length. The arc length parameter has the property that if you use the arc length parameter to parameterize the curve, the tangent vector is always a unit vector. So that's the defining characteristic of the arc length parameter. And in this derivation, we have this combination of coefficients that's called the Christoffel symbol of the second kind. So this is how we arrive at the Christoffel symbol of the second kind. And in other textbooks, there are different ways to define the Christoffel symbol, but this is the approach that we take. Okay, that is through the equation of geodesic. So in particular, the derivation for the geodesic equation is fairly involved, fairly complicated, but if you it's a good exercise for practicing the properties of the metric tensor, the summation notation, and all of that. Okay, so I'm just going to import pretty much all of this because we will be doing more examples today. Because I mean, we've been seeing a lot of theory crafting, but I just wanted to do more computational exercises, just like in regular calculus, right? If you just go about proving theorems all the time, deriving formulas, deriving all kinds of differentiation rule without applying them, these will still feel rather foreign to you. That's at least just my opinion. Okay, so let's get started with seeing more examples. So these examples aren't in the textbook, but these are just my examples that seems rather obvious to me. You should apply this theory to these examples. So this is our homemade example. So for our homemade example, I'll just write EG. Okay. For the examples in the book, I will label it with numbers. So let's start from just the Euclidean plane, 2D plane with the polar coordinate, and see how this turns out. So before doing any actual calculation, let's first think about what we should expect. Because this is just a 2D plane, Euclidean plane, with the polar coordinate, the geodesic, of course, are straight lines. And actually, it has nothing to do with the fact that we use the polar coordinate to study the 2D plane. Geodesic on the plane should just be straight lines. Right? So every middle school student knows that. If you could say fix 2 points, you put 2 points that distinct, what would be the path that minimizes distance? Well, it has to be the straight line segment, although there's not much proof at that level, but it should be intuitive. We hope to recover this result. Okay, so that's what we're getting at, right? So what we expect, our expectation is geodesic are straight lines. So let's work out the machinery and see how that actually turns out. expectation geodesics equals straight lines. Okay, so here's the polar coordinate. So I mean, I'm just drawing a sort of a background Cartesian coordinate. Of course, this will be discarded very soon. Just for the purpose of defining polar angles and stuff. So this is r and this is theta. Okay, that's the polar coordinate. And let's imagine if we change r and theta by a little bit. So if you keep r constant and change theta a little bit, it means a slight rotation, a small rotation of the radius vector. So it becomes, the new position is now something like this. This is d theta, and this is the displacement in the theta direction. Because r is constant for now, there is no displacement in the radial direction. Of course, this is just r d theta. Very intuitive. And now let's say if you make a radial displacement, say dr, like this. Right? And what would be the total displacement? So you can think of, you can see there is an approximate right triangle going on. This is an approximate right triangle, and ds, you have ds squared. So ds squared equals dr squared plus r d theta squared. So it will be r squared d theta squared. So that will be the line element. For the purpose of applying the formulas we stated earlier, we're going to denote x1 as r. So x1, x2 will just be r theta. R theta, okay? And just to emphasize the subtlety we mentioned earlier, that what we do is essentially local. Because polar coordinates can only cover a subset of the R2 plane. Remember, when x and y is 0, x and y, or the x1, x2, not x1, x2, but rather, yeah, x and y are 0. When x and y are 0, namely at the origin, polar coordinate cannot represent it because theta is not well defined there. R is 0, but theta is not well defined there. The coordinate must have a one-to-one correspondence between itself and the points on the actual space. So what polar coordinates can cover, so to say, what polar coordinates can cover is R2, the 2D plane, minus the origin, and that's an open set on R2. So the polar coordinate is only a local description of a subset of R2. Of course, R2 admits a global coordinate. R2 does admit a global coordinate. That's the xy, the Cartesian coordinate. But in general, a coordinate system on a Riemannian space can only cover a subset can only describe a subset, okay, which is totally okay. Anyway, so here we have our line element, and from that we can write down our metric tensor. So what would be Gij? Our Gij, looking at the formula here. Okay, so looking at the formula Gij, because x1, x2 are dr and d theta, right? Sorry, x1 and x2 are r and theta. Gij would be the 2x2 matrix 1, 0, 0 r squared. That's the metric tensor. You can read it immediately from the quadratic form of linear line element. This is Gij matrix. And then let's do the inverse matrix, or the reciprocal tensor, or contravariant metric tensor. Same thing. This is a matrix inverse of Gij earlier, so this will be 1, 0, 0, r to the minus 2. It's a diagonal matrix, so calculating inverse is very easy. Oh, actually, here, I mean, So sorry, I didn't catch up with chat. So first of all, I am not a professor. Okay, I don't have a PhD. So, but thank you very much for addressing me this way. But seriously, I am not a professor. I'm just a guy trying to improve, really. Okay, this is not a lecture. This is me trying to review some of the stuff we learned earlier. I learned earlier, like 10 years ago, and hopefully still can make sense out of it, because I'm preparing for an upcoming stream on information geometry, which shows up next week, which comes up next week. So yesterday I asked what's your background. I didn't say. Yeah, so yesterday I believe I only mentioned it very quickly and then I move on to other topic. Yes, I did answer my background yesterday. My background is as follows. I had my undergraduate study in statistics and applied mathematics, and then later I did my master's degree in applied mathematics, and now I'm not in academia, but I work in the industry as applied mathematician and data scientist in the retail industry. So there's that. So even though I left university, not in academia, but I still study and teach mathematics, teach, or to say more appropriately, tutor mathematics. Tutoring is more like a semi-regular thing, but self-studying mathematics has been consistent. In where it doesn't matter where I'm in uni or after. So Nova, are you a grad? Well, I just answered that question. I was a graduate student. I have a graduate degree. I have a master's degree in particular. I don't have a PhD, and I don't know whether I would ever consider getting a PhD, given other priorities in life, but it is certainly an option. Okay. Anyway, thank you guys for your questions in chat. And yeah, sometimes I just go about talking math and I forgot to read chat. Sorry. And I will try to answer questions more promptly. Okay, so right now I'm just trying to do this example. So in a 2D plane with a polar coordinate system, so these are the fundamental ingredients. Really just one fundamental ingredient, the line element. The line element dictates the metric tensor and conversely. And with a metric tensor, you have the reciprocal metric tensor or the contravariant metric tensor, and or you can derive Gij, the original metric tensor, from the contravariant metric tensor as well. So these are all equivalent description of the same thing. Okay. So with that out of the way, we can calculate the Christoffel symbol, right? So let's calculate the Christoffel symbol. So yesterday we discovered a method to, not a method, but rather a mnemonic. Like how do you memorize this complicated formula? Or not just say memorize, but rather like a memory aid, so to say. Because fundamentally speaking, yeah, okay, well, if you do say so, then, well, no, I mean, although a simple first name Ming would suffice. But thank you very much. So yeah, the string froze because of crappy internet connection. But yeah, to answer the question by Nova, thank you first of all, thank you very much for joining the stream. Yes, operation research is a field in applied mathematics, and it is actually a very big one. Overall, I mean, it's just my opinion, okay? It's just my personal opinion that applied mathematics can be rough. Hi, yeah, it's stuck. It's stuck. It's freaking stuck. Sorry, guys. It's just the internet is very unstable. Is it down again? This is insane, bro. Okay, anyway, so yeah, here we should have G Yeah, it came back. It came back. Okay, great. Okay, hopefully this is the last time. So here we have gamma. You have gamma 1 1. Or guys, do you think gamma 1 1 is better or gamma r is better? So we're treating r as a label here. Perhaps gamma 1 1 1 is better, because if you write gamma r, you still might think of r as a variable, but it's just really just a coordinate name. And 1 and 2 serves the same purpose. So I guess 1 is faster to write, so I'll write gamma 1 1 1. What I'm saying is there should be 8 numbers. There should be 8 numbers because each index has 2 values, 1 and 2, or r or theta. So 2 times 2 times 2 is 8. Gamma 1 1 1, gamma 1 1 2, gamma 1 2 1, gamma 1 2 2. Okay, and now you have gamma 2 1 1, gamma 2 1 2, gamma 2 2 1, and gamma 2 2 2. Okay, so we need all these values. So by the formula, so the formula actually have this structure here. You got the 1/2 factor. That's always there. And the first g is a contravariant g, okay, whereas all the other g's are covariant g. So put a g here, and the index of the contravariant g is as follows. One index is the upper index in tau. So sorry, one index is the upper index in big gamma. Big gamma always only have one upper index, so we put a 1 here. And the other index is the dummy index being summed over. So let's put a sigma here, just like in the formula. And then you have dg. So let me just write dg over dx first, and then put the indices together. Put the indices, return all the indices later. Okay, dg over dx. Got 3 dg over dx's. Okay, and let's write the last one first, because in the last one you have a minus sign. The term with a minus sign. The indices for g are the indices in the lower index of big gamma. So here we have gamma 1 1 1 at the bottom, so you just put 1 1 in the last g. And the x associated with that particular little g has an index of just the dummy index, the sigma. Okay, so there's that. And the first two terms, the two terms with a positive sign in the bracket, will have a dummy index sigma. So let's write that, sigma, sigma, and the indices downstairs, 1 1. You see here you have alpha and beta alpha. So you just add 1 here and 1 here, 1 here, 1 here. And by the way, because of the symmetry, G is a symmetric matrix. Okay, G is a symmetric matrix, so it does not matter if you write G sigma 1 or G1 sigma, they're the same thing. Okay, so let's just evaluate this expression. So looking at the expression, we notice because of the dummy index, there is a summation implied. And sigma, of course, runs from 1 to 2. So really, this is a sum of 2 terms in summation notation. Okay, when sigma equals 1, okay, when sigma equals 1, so G, you got G11 over 2 times dG11 over dx1, which means dx1 is just dr. Okay, dg11 over dr, and then plus dg11, once again, sigma equals 1, dg11 over dx1, which is dr, and then minus dg11 over dr, right? Sigma equals 1. Right? When sigma equals 1, this is the term you get. When sigma equals 2, think about what happened. When sigma equals 2, you got g of 1, 2. So g of 1, 2 is just 0. So there's no second term. So now let's evaluate this and see what happens. So g11 is 1, which is a constant, which means all the partial derivatives of g11 are all 0. So this is just 0. So we're done with this coefficient. And gamma 1, 1, 2 would be as follows. So you have G1 sigma over 2 times dg over dx. Once again, just like what we did earlier. We'll worry about the indices later. Okay, 1, 2 in the bottom of big gamma, so you get dg1, 2 over dx sigma. Okay, and then put the sigma in the little g, and the first two terms, 1 over 2, 2 over 1, interchange. Okay, so there's this pattern going on. All right, so looking at this expression, of course, you just need to write down the terms of the summation. As earlier, only one term is non-zero. Only one term is non-zero, so you get just g11 over 2, and then dg11 over dx2. dx2 is theta, x2 is theta, and then plus dg12 over dx1, which is dr, and then minus dg12 over dx1, which is just r. The second term vanishes because of g12 is 0. In fact, due to the fact that g12 is 0, the first 4 Christoffel symbol numbers all have exactly one term. Remember, the factor, this very factor, g1 sigma, is universal for all those 4 terms because 1 corresponds to this one, okay? And yeah, and because of that, so you always get g1 sigma at the beginning upstairs, and for that reason, the second term, g12, is always 0. You don't need to write. Okay, so is this non-zero or 0? In here, g11 is 1. g11 is 1, but it's a constant, so the g11 which over theta is 0. Is 0, and here you have g12 is also 0, so this is 0. Actually, guys, I need to take this phone call, and I'll be back in 3 minutes, and hopefully I'll be back as soon as possible. This should be not terribly important, but let me just make sure. I'll be back. Sorry, guys. Sorry, guys, about the earlier disruption, and I'll have to leave, okay, for a few minutes. All right. Hi, I'm back. Thank you guys for waiting, and let's continue with the calculation. So the third one is now g1 sigma over 2 times dg over dx. I strongly recommend, if you guys are serious about learning tensor calculus, do this calculation with me. dg over dx, 2, 1 at the bottom, and then sigma downstairs. Okay, sigma 2, 1, 1, 2. Okay, that should be okay. And now you have g1 1 over 2. Here this is dg 1 2 over dx1, which is dr, plus dg2 1 over dx2, which is d theta, minus dg2 1 over dx1, which is dr. And all the diagonal terms, all the off-diagonal terms are 0, so this one is 0, 2. Okay, gamma 1 2 2, so you get g1 sigma over 2 dg sigma dg over dx plus dg over dx plus dg over dx. Worry about the indices in a minute. Dg over dx. The last dg has a 2 2 subscript, and the sigma is attached to x. And the first two terms, we got sigma here, 2 here, 2 here, 2 here, 2 here. Okay, and just one term, so g1 1 over 2, and this is dg 1 2 over d theta plus dg dg 1 2 again over d theta again, and then minus dg 2 2 over d r, over dr when sigma is just 1. So here you see something rather interesting happens. So g1 1 is just 1, so 1 over 2. The off-diagonal terms g1 1 and g1 2 g1 2 cancels, but here something interesting happens. So you got dg 2 2 over dr. g22 is r squared, finally a non-zero, yay. So this is minus 2r, so this is just minus r. Okay, so that's a non-zero. Let's continue. Okay, so these four values with the upper index 2. Okay, yeah, just follow the recipe here. g2 sigma, but really you just need g2 sigma over 2. Actually, can we be lazy and save this step? Actually, let's do it once. Okay, g2 sigma over 2. I forgot who said this, but I remember seeing a short sometime earlier. I think it was said by an Oxford mathematician during his lecture on Fourier series or something like that. He said, in order to be a good mathematician, you have to be lazy. Just interesting. So dg over dx plus dg over dx minus dg over dx. Okay, 1 1 here, 1 1. No, it's not 1 1, but sigma 1 1 1 1. Okay, gamma 2 1 1. What does this lead to? Well, first of all, you just need g22 over 2. Here's over 2, and this will be dg22 dg21, sorry, over dx1. dx1 will be just dr, and plus dg21 over dr. So these two are 0, and minus dg11 over d1, dx1, which is dr, and this is 0 as well because g11 is constant, so this was just 0. Okay, so let's now try to be lazy. Let's now try to be lazy here. So we know that the first factor, it has to be half G22. It's all the same for these guys. Okay, and then let's write down the dg over d thing. Okay, we still don't know which variable yet, but just write dg over d. Dg over d. Okay, so here, according to the pattern we've seen earlier, the last g should have subscript of the subscript in big gamma. So the last one will have g12 here. And which coordinate? Is it x1 or x2? Well, it should conform to the summation index, right? Sigma is the summation index, and here we said only the summation index sigma equals 2 matters. So it would be dx2, which is theta. Actually, did I do this wrongly? I think I did it wrong, right? Here it should be theta. Above it should be, why did I write r? That's a mistake. Because when sigma equals 2, I got this factor g22. Otherwise, it's just 0. Right. So g22 is here. So this means I should put a dx2 here. dx2 should be theta. Yeah. So it doesn't matter. The result is still correct because g11 is still constant relative to theta. Okay. So now let's figure out the earlier terms. What about the earlier terms? Well, we just established that sigma is 2. Sigma is 2, so the first two partial derivatives should have a subscript of 2. And the lower indices are 1, 2. So it should be 1 here, x2 down here, 1, 2 here, x1 down here. X1 down here. So that should be correct. Let's double check. Okay. So there's the upper G, upper index G, should be G22. Yeah. So sigma is 2. Hence the last term. Okay. There should be 1, 2. One of the indices in the first two G terms should be 2. Yeah. And then 1, 2 alternate. dx2 over dx1. Sorry, dg21 over dx2 plus dg22 over dx1. So this looks correct. dx2 is just theta, so change that to theta. And dx1 is just dr, change that to dr. Okay. So now we can save some writing here. Okay, so the advantage of index notation is that it largely tells you what the formula should look like. This is an excellent bookkeeping device. Okay, so here you have half g22 is r squared. g22 is r squared like this. Okay, we've seen that. And then this is a cross term, so it vanishes. This is a cross term, so it vanishes. And then times dg22. Actually, my bad. G22 upstairs. This should be G22 upstairs. Upstairs should be this. R to the minus 2. My bad. Not G squared. This is G22 upstairs. Be very careful. This is G22 upstairs should be R to the minus 2. Okay. So these two terms goes away, and dg22 over dr would be 2r. This is 2r. Okay, and then cancel. You get r to the minus 1. So that's done. Okay. Following this pattern, let's do the same calculation. You get g22 over over 2 times dg over d something plus dg over d something minus dg over d something. Right? Okay, so lower indices or big gamma is 2, 1, so put 2, 1 here in the last term. And because of the summation index, sigma equals 2, so you should put dx2 down here, which is d theta. Okay, we just established that the summation index sigma can only be 2. sigma can only be 2, so you should have a 2 here, 2 here. Here, you have 2, 1 here, so it's g, you put a 2 here, dx1 here, and put a 1 here, dx2 here. x1, of course, is just r, so change that. And x2, of course, is theta, change that. Okay, evaluate. Evaluate. Cross term goes away, these two terms goes away. And here, dg22 over dr, oh, isn't that just we calculated earlier? This is 2r. So this is the same as the earlier one. R to the minus 2 over 2 times 2r. You get r to the minus 1. These two are non-zero and are the same. Excellent. Gamma 22. What's gamma 22? Well, so skip this intermediate step. G22 over 2, that hasn't changed, times dg over d something plus dg over d something minus dg over d something. Alright, so put 2, 2 here. Summation index is 2 again, so this is again d theta. Okay, and here summation index 2, so we put 2 here, 2 here, and the index are all 2, so it's 2 here, 2 here, and dx2 is dx is d theta. So this is theta here. Okay, and because g22 does not depend on theta, so g22 is r squared, does not depend on theta, so the last three derivatives all vanishes, so it just gets 0. So these are the 8 Christoffel symbols. Okay. So you get the Christoffel symbols. Let's write down the geodesic equation. So this is the geodesic equation. Here. This is a geodesic equation. And there should be 2 of them. Okay. There should be 2 of them. So because x1 should be actually, you know what? We'll write down the original form and then we will translate to our coordinate. So it would be x double dot 1 plus gamma 1 alpha beta x dot alpha x dot beta. That's the first equation, and then you have x double dot r plus big gamma 2 alpha beta x dot alpha x dot beta equals 0. Okay, so those are the 2. So because the first equation, the upper index is just 1, so the summation only involves the first 2 terms. Okay, and the only term that's non-zero is just the last one, big gamma 1 to 2. So therefore this is just x double dot 1 plus, all right, big gamma 1 to 2 x dot 2 x dot 2 x dot beta. Right. So here, because of the summation convention, there should be 4 terms in principle. However, because of only big gamma 2 2, big gamma 1 to 2 is non-zero. There's only 1 term. Okay, awesome. The next equation. So you got x double dot r plus gamma to alpha beta. Remember, gamma to alpha beta for all alpha and beta has 2 non-zero terms. So it should be gamma 2 1 2 x dot 1 x dot 2 plus big gamma 2 2 1 x dot 2 x dot 1 equals 0. Right, I forgot equals 0. So simplify or rewrite it into more natural notation. x1 double dot would just be r double dot. R double dot, and then plus gamma 1 to 2. What's that? It's just minus r. This is minus r, okay? And sorry, what's x What's x dot 2? X dot 2 is theta 2. Oh, I forgot to change beta to 2 here. So this is just theta dot square equals 0. All right. So there we have that. And lastly what we have. X double dot r, x double dot 2, that would be theta double dot. Yeah, and then plus, those two terms should be the same, because gamma 2, 1, 2, and gamma 2, 2, 1 are the same. So it's 2 times r to the minus 1 times x dot, okay, times x dot, and then times theta dot equals 0. So that should be it, right? This should be the geodesic equation. But what does this mean, though? Right, can we solve it? I mean, it's a nonlinear system, but we know from earlier, not from earlier, but just by our intuition, the expectation is that geodesic should be straight line. Does it look like straight line? It better be, right? Otherwise, it's awkward. What I found interesting is that this feels like the acceleration formula in polar coordinates. Guys, let me just do this derivation real quick. This feels like acceleration equals 0, which exactly should be straight lines, but I can't seem to be able to solve it from these equations. Or can I? Can I say, for example, eliminate one variable and just have a scalar ODE? Not a scalar, yeah, but not a well, I want to decouple the system, is what I mean. Can you do that? X double dot is r times r. How can you decouple the system here? It's like if the acceleration is 0 in the Cartesian coordinate, solving it is trivial, just integrate it twice. How do you solve that in the polar coordinate, though? This is awkward. Okay, here, this is a side tangent, but basically acceleration, I want to derive the acceleration in the polar coordinate real quick. In polar coordinate. This is a example, sorry, not an example, but a classic derivation in mechanics, acceleration in polar coordinate. So imagine this, have x and y. The helper or background Cartesian coordinate, and this is the polar coordinate. Right, the real question is just how to interpret this result, right? This is a geodesic equation, which I believe is a straight line, but I can't seem to solve it rather in an obvious manner. Okay, so this is r theta. X is r cosine theta. Y is r sine theta. Okay, so these are the conversion rules, right? And let's say a vector r. A vector r is what? A vector r is the radial length, right? R times er. Okay, er means the unit vector in the radial direction, like this. This is er, and it points in the direction such that r increases, like this. And now you have e theta. E theta is the perpendicular component. The perpendicular component. So a key difference between the unit vector, the unit or coordinate vector in polar coordinate versus Cartesian coordinate is that the unit vectors changes from point to point. The Cartesian coordinate, in Cartesian coordinate, the unit vectors don't change. Oh, no worries, quant guy. I should make a stochastic calculus live stream soon. You know, video making has been dormant for a few weeks now. I should really catch up with that. Yeah, I'll keep doing more financial math. Like, perhaps we'll do a Shrev stream. You guys, if you are interested in financial math, chances are you know Shrev, right? Shrev Volume 1 and 2. There's only one explaining it for people like me. Okay, no, thank you very much. Like, I mean, what do you mean people like you? Like, what's your background? I'm interested in my audience's background. Like, what is your say what is your goal and that kind of thing. You don't always. I mean, I'm less interested in your say degree, although that can be informative in some sense. But just say like how familiar are you with basic calculus and probability. I mean, I don't ask for measure theory, so yeah, that kind of thing. Yeah. I mean, yeah, you can think of an answer and yeah, it doesn't matter. So I was trying to figure out, this is an equation for geodesic in the software engineer from Pakistan, want to be a quant. Okay, great. Okay, great. Yeah, great. So, okay. Actually, you know what? Because recently I started this series on proof writing. I might as well call it proof writing for applied scientists, which might be a little bit controversial because typically you don't associate proof writing with applied scientists, but I deliberately wanted to break that stereotype. Okay. I want to be a quant in a quant firm. Yeah, totally, you can do that. So because I feel like there's already a lot of great programming channel, and a lot of my people, not my people, but my audience are actually from SE background. I figured I'll just focus on the math, right? If you guys understand the fundamental principles, then you can code the formulas or the algorithm yourself. So I'll just do derivations and manual calculation to hammer the fundamentals and main intuition. Okay, so here I'm trying to interpret what is going on here with the geodesic equation. And this is a position vector. This is a position vector, and then we can differentiate to get the velocity. So velocity would be r dot. And as I mentioned, a key characteristic of the polar coordinate is that the unit vector er and e theta changes from point to point. So to do differentiation, you got to keep that in mind. Not only r changes, er also changes. So that's why we need the product rule. That's, you get r dot er plus r er dot. Okay, this is a velocity. So which brings us to the question, what is er dot? What is er dot? So er dot, question, and of course this needs to be answered. What needs to be answered is that what is er dot and e theta dot. We haven't seen this one yet, but I have a feeling that this will pop up. So what is e theta dot? Right, so think about that. And here's a quick way to answer that question. So because of the geometry, we can actually express er dot and e theta dot in terms of the helper Cartesian coordinate. So draw the picture. This is er, and this is e theta. This is e theta, and here, this angle right here is theta. In the vertical direction, you got EY, right? This is EX. These are all unit vectors. So from the geometry, okay, you can see ER equals cosine theta. Just do vector decomposition. ER equals cosine theta times E theta, EX, plus sine theta times EY. Okay, and what about E theta? Well, E theta is, from the picture you see there's a minus component, minus sine theta, EX plus cosine theta, EY. So you have these geometry, and the nice thing about EX and EY is that they are constant. That's the nice thing about Cartesian coordinates. The unit vectors stays constant. The unit coordinate vector stays constant everywhere, right? So now you just differentiate. So this way you get ER dot equals what? Well, ER dot equals cosine dot, which is minus sine theta times theta dot. I keep doing the basic stuff, learn and forget. Secondly, sources is a problem and guidance. Not a lot of good courses online that covers everything from basic to advanced stuff. Okay. I mean, covering everything is always a very ambitious goal. I'm not even claiming that I cover everything. I try to be as thorough as possible, I guess, but the best way to learn and not forget is to just derive everything. It's just to derive everything. Derive everything in a way that not memorizing, okay, but feel like this is inevitable to you. So it's like now when you start first learning arithmetic, you probably need help from addition and multiplication table. I always use this example. But then you later on you just reach to this level that you don't need a table to do arithmetic. It might still take you a long time to do it. Let's say if you multiply, let's say, two 10-digit numbers. I mean, it's a basic arithmetic problem, and it may take you a long time to get to the answer. But you can do this totally independently without any external references. So this is how knowledge became yours. I guess that's how I can say about that. Okay, so the first term differentiating, after differentiation give you minus sine theta times theta dot times EX, and the second term is cosine theta times theta dot times EY. And notice what the hell this is. Okay, this is exactly E theta times theta dot. This is exactly theta E theta times theta dot, like this. And there's actually a geometric interpretation for that. So imagine if you just change theta by a little bit. Let's say you make a small rotation. You make a small rotation. So what would be d theta? What would be the little change in DER? So this is DER. DER is exactly in the rate, is in the what? Is in the angular direction, perpendicular to this one. And then times the rate at which theta changes. So this is the new ER. If you change theta by a little bit, this is the new ER. So the new ER minus old ER is this DER, and DER is in the direction of E theta. Okay. And the size of that is exactly how fast theta changes. Okay. All right. So this is ER dot. And now let's continue with the E theta dot. So E theta dot is differentiating E theta, and you get minus cosine theta times theta dot EX plus cosine theta dot, which is minus sine theta times theta dot, and then times EY. So this way you get minus ER theta dot. So E theta dot is minus ER theta dot. Okay, so let's take a look at what does that, why is that the case, right? So if you change theta a little bit, say, and E theta would simply become a little bit more rotated like this. It's the same principle as earlier, really, right? So this is the little change in E theta. This is d E theta. As you can see, it is in the opposite direction of the original ER, so hence the minus sign. Sir, do you have a recommended book to learn all math needed to trade using math? I mean, I'm not a, let's say, algorithmic trader or anything. So, but for fundamental, you mentioned probability, right? Probability and stats. I always use this book for live stream, and I strongly recommend it to everyone. And it's completely free. So that's a book, probability book with an aim towards statistics. So perhaps that's useful for you. Let me know if you have something more concrete, so to say. Yesterday, I tried to look into stuff on algorithmic trading. Perhaps I'll make a video on that. Not a video, but a live on that. Because you can think of these lives as me preparing for videos. This is what it's really about. So this is why I don't spend an awful lot of time doing just random hangout stuff. It's always almost always like intense math. But you can think of this as my attempt to break my writer's block, basically. And you might wonder why there's been so few videos, because I'm kind of stuck. And I need practice myself. When you become a math creator, it really demands a stronger foundation of math than you are used to, because say if you can only apply it but you can't explain it, then you can't make a video. So I'm just trying to make things as pedagogically sound as possible. So yeah, this book from probability and statistics, and I think it's a great book for, say, people already have backgrounds in, say, just STEM in general, science, technology, engineering, mathematics. However, we wish to come back to the more fundamental part of the subject, right? And there are things that you feel like you know, but you can't apply it accurately, right? There's always this temptation to say, oh, I heard of this term before, I've seen the formula, so I must be able to apply it. Well, we don't know. Like, go check yourself. Like, this is very concrete problems, and the solution manuals are also available here. Yeah. So this one, probability and statistics, and usually we do live streams on this every day. Not every day, but every Saturday. Now, before it was Sunday, but nowadays I tend to switch to Saturday because Sunday I have personal responsibilities. So yeah, currently we're on chapter 6. Well, we didn't start from the beginning. We did chapter 5 a while back, and I do plan to cover 6, 7, and 8 as an introduction to mathematical statistics, likelihood inference, Bayesian inference, and optimal inferences. So this is what we wanted to do. And after that, we'll probably switch to more fundamental models in statistics, such as linear models. The fundamentals of linear models is all very going to be so focusing on the linear algebra, the distribution. So once again, this is just how we do things on the channel. Like, we tend to use just a piece of whiteboard and derive from scratch, do the manual calculations, get the intuition, and then you can decide what you want to do with it. You can pick your favorite software package, fit it to your problem, and decide whether or not the model is appropriate at all. So I hate to do this kind of black box learning. Okay, because this is a package, this is a data set, type these lines of code, get these diagrams, and call it a day. I think that's very meaningful. All right. So here's the question. It says, I get dizzy when I see a differential equation like the one you're solving. It's okay. It's okay. It takes, yeah. So I mean, it's like here. I will just be honest here. Okay, we're doing tensor. This is advanced undergraduate / graduate stuff. Probably more advanced undergraduate. So I mean, not every math major would take this. Not even all math major would take this. Let's just be honest. I learned this stuff like 10 years ago when I was still in uni. But later on, I gradually, because I pretty much I never used this stuff in actual research or industry, right? So my knowledge for that started to decay, basically. But now I wanted to get back. For all kinds of reasons, I wanted to get back. So this is basically me reviewing this stuff and see how much it still makes sense. Because in a uni, you can kind of get away with not knowing the details with the fundamentals, right? You can kind of get away with, oh, here's the formula, just apply it and get the right answer and move on with your day, right? But if you're a creator and you're serious about it, I tend to think of me being a self-serious person, so I don't want to just give the formula and declare that a rule and just apply it and move on with your day. I want to show the intuition behind it, and viewers can walk away with a video with a sense that they could have discovered it by themselves. They could have, right? They could have. So I wanted to discover a logically natural route to various math concepts so they feel natural. Okay, this is what I'm trying to get to. However, because we don't always learn things that way, right? We don't always learn. So sometimes you just, let's be honest, sometimes you just want to get the grade and move on. A lot of people do that, and I was one of them when I was in uni, because there's so many damn courses to take, and you can't afford to sit down on a single notion and spend days and nights thinking about the original motivation, like how do you derive it from scratch. It's just not very compatible with the university schedule. Right? So, but when you're a creator, I wanted to do things a little bit differently. So people who want to know the fundamentals in a, so to say, in a way that that can be internalized, I feel like this is what I need to do. So anyway, so where did you go to uni? I went to University of Waterloo in Canada. I don't usually spend a lot of time on formal credential, but you're interested, here's this. I took a GR course in Christoffel symbols, tensor compression in my freshman year of fall. Okay, wow, freshman, that's pretty intense. Good for you. So here, yeah, we're coming back to this. We're trying to make sense out of this equation. Okay, so it's hard for me to think of how do you actually say solve this in a forward manner. The physics major, it was graduate course. Okay. Yeah, we pretty much currently do things the physicist way, okay? So all those indices, geodesics, but yeah, perhaps in the future we'll come back to this matter in a more modern way, okay? In a more quote-unquote modern way, but still, this is still fundamental for applied sciences. Tensor calculus still dominates the literature in physics and engineering. So as applied scientists, as applied mathematician, we should be able to understand this stuff from both a classical and modern perspective. Okay, so here we have this two useful formulas, the r dot and theta dot. Let me just put it on the side. Okay, so r dot on the picture, you got r dot, E r dot equals E theta times theta dot. Okay, that's cool. And E theta dot equals minus ER theta dot. I'm just going to box these two formulas. Okay, so this is useful for velocity. Okay, this is useful for velocity. So velocity, therefore, r dot vector is scalar r dot times ER, and then plus r times ER dot. ER dot would be E theta times theta dot. And at this point, there's nothing else to simplify because ER and E theta are linearly independent vectors. So it's like EX and EY. Right? And this is connected to our formula for ds. So imagine what would be if this is velocity, right? Then the speed would be velocity length squared. And because ER and E theta are orthonormal bases, so this would just be r dot squared plus r squared theta dot squared. And this is exactly equivalent to the infinitesimal length squared. ds squared equals dr squared plus r squared d theta squared. Okay? So that's exactly the metric tensor. So basically you can recover the metric tensor using basis vectors, is what I'm saying. And we'll do this actually in a second example, which is on the sphere. But you can start this. You can start from here and just do everything in the metric tensor. or you can derive the metric tensor using the basis vector. Both are okay. So, but what we really wanted to obtain is acceleration, because it has to do with second order derivative. So let's do that. This is a velocity. Okay. This is a velocity. The same. And this is speed. This is squared speed. Okay. And this is line element. Same as what we have from the beginning. Okay, so there's the these quantities, and now let's do the acceleration. So the acceleration will be as follows. Therefore, you get the acceleration. This is a r double dot, r vector double dot. Once again, use the product rule. You get an r, no vector sign double dot times er plus r dot er double dot. Sorry, er dot. Er dot, and then plus r dot. So here you have three terms. For the three terms, the product rule is similar. So you differentiate one factor and keep the others unchanged, and just alternate and do so for every single term. So you differentiate the first term, first factor, you get r dot, and e theta and theta dot don't change, so keep them here, and then plus r times e theta dot times theta dot, and then finally plus r e theta times theta double dot. Okay, that's the product rule for the second term. There's three terms in total. So now let's use the expression for er dot and e theta dot. So we derived these earlier, and now they're paying off. So you got r double dot er plus r dot. What is er dot? Well, that's e theta times theta dot. Okay, and then plus r dot e theta dot. This term, nothing needs to be done for this term. Okay, then this fourth term, there's a theta dot there, so you got to substitute that. So r times theta dot is er minus er theta squared, right? So you get, this is er theta dot squared here, like this. And the last one would be r e theta double dot. All right, collect the terms, and you got the r double dot e theta, sorry, r double dot er. Okay, er, what are the er terms? R double dot minus r theta dot squared, theta dot quantity squared times er. So that's the radial component of the acceleration, and then plus 2r double dot, no, not double dot, single dot, r dot theta dot. Okay, and then what's that? And then plus r theta double dot, r theta double dot times the unit vector in the tangential component, or tangential direction, to get e theta. So that's the formula for the acceleration. Right. So physically, this is meaningful. R double dot tells you how the radius changes, the scalar radius changes. Of course, the fact that if the scalar radius has an acceleration, it would contribute to the radial acceleration. It makes total sense. However, even if r is constant, even let's say there is no radial acceleration. In fact, let's just say if the radius is constant, from basic physics we know in the radial direction there is still acceleration. This is called the centripetal acceleration, which is exactly this one. Minus r, in the minus sign stands for in the minus direction of er. It points towards the center, and then times the radius and the angular velocity squared. That's the centripetal acceleration. So this is meaningful. And here, in the last term, you got e theta term. Right? This is the tangential component of the acceleration. It's also physically meaningful. So the last term is easy to understand. So imagine if r is constant. Imagine if r is constant and the theta is accelerating. Of course, this will contribute to acceleration in the theta direction. However, even if, let's say, the your theta double dot is 0. There could still be an acceleration, and this is the Coriolis acceleration. This is the Coriolis acceleration. 2r dot theta dot is the Coriolis acceleration due to the interaction between the derivative here. You see here in the velocity vector, the differentiation leads to these two terms. I mean these two groups of terms. These two groups of terms, by their interaction, creates this extra, this two factor. Two factor comes from the interaction between the two terms, and that's the Coriolis acceleration. Okay, because let's say if r is changing, and theta dot is constant, this will create a Coriolis acceleration. This is important in, say, climate modeling, as well as military applications. So, for example, long-range shooting needs to take the Coriolis effect into the account. So that's the acceleration. So let's compare the acceleration formula with the geodesic equation. So this is a geodesic equation. Do we see anything similar here? We spend all that time deriving the acceleration in the polar coordinate. Do we see anything similar here? The first one just says the component of the acceleration in the radial direction is 0. And the second just says in the tangential component that's also 0. Because you can multiply r on both sides and you get exactly the component in the theta direction. So now this mystery is finally solved. This just means the acceleration, even though solving this equation is difficult, decoupling it is difficult. It has a meaning. I mean, it's not obvious, but it does have a meaning. It just means the hi, thanks for joining the stream. The acceleration equals 0. I mean, of course, from Newtonian mechanics, we know if the acceleration is constant 0, then the line is a straight line, which confirms our expectation that geodesics are straight lines. Hi, thanks for joining the stream. So yeah, acceleration equals 0 just means straight line. I know this is perhaps a little bit convoluted, a convoluted way to get to this conclusion, but I mean, unless you have a better way to decouple, I mean, you have a better explanation, so to say, you can decouple the system and actually solve or maybe you don't have to decouple it, just solve this differential equation. I guess in classical mechanics there is a way, right? In classical mechanics, it's usually, how do you do that in classical mechanics? In classical mechanics, there is a trick. So if, let's say, the force is radial, like the force, the gravitational force, Earth, between Earth and the Sun. So if you place the coordinate at the Sun's position, the force is radial. The force is radial, therefore the torque is 0. The gravitational force acting on Earth has 0 torque, and as a result, it's got this property of angular momentum conservation. Angular momentum conservation translates to the Kepler's second law, equal area law. So I think we can do something here. Equal area law should correspond to this one. Here, let's get to the, if you just look at the equations themselves, okay, without this physical interpretation. From this equation, from 1 and 2, okay, from 2, you can get, multiplying r is a major inspiration. So let's do r theta double dot. Actually, yeah, theta double dot r plus 2 r. Actually, you know what? I'm going to multiply by r squared. Multiply r squared. I know this is a trickery. Theta, yeah, it's because it's inspired by physics. The area law needs an r squared. R squared times theta double dot plus r times r dot times theta dot equals 0. And this is exactly an exact differential. This is d over dt. Theta dot times r squared equals 0. Equals 0. And that's the equal area law. And if you want to be super nice, if you want to be super geometric, let's multiply by half r squared. Let's multiply by half r squared. So this way you get d over dt of half theta dot r squared being 0. And that's exactly the... And what on earth is this? Well, going back to the geometry, that's the area speed. So imagine in the polar coordinates, you have a curve like this. This is r of theta. Actually, you know what? This is a parameterized curve. R as a function of t, theta as a function of t. It's a general curve. So how fast does it sweep area if you consider this, right? This is the sweep area. In a small time interval, this is the swept area. Does that make sense? Right? So you can think of this as a right triangle. Let's think of it as a right triangle because this part is negligible. Is negligible, okay? So the area is exactly, yeah, this is the area rate. So this angle is d theta. So the height, to this infinitesimal height of the triangle is approximately r d theta, and this is r. So the area, dA is half r times r d theta, which is half r squared d theta. So dA over dt, the area speed. The area speed would just be half r squared theta dot. This is exactly the same. This is a dot. So the area speed is constant, so we can use that as a first integral to solve this equation. So here, therefore, from 2, you get this. So you got half, let's say, half theta dot r squared equals a. Let's just call that a constant. Okay, this is just not right. Equals a constant. So can we use that in our first equation? Well, let's substitute theta dot, shall we? So therefore, from here you get theta dot, which can be solved from 2a over r squared. Which makes sense because remember the Kepler's law from classical mechanics. Right? Because of the conservation of angular momentum or conservation of the area speed, when the planet is closer to the star or the sun, its angular speed is faster to keep the swept area rate constant. And when it's further away from the sun, the angular speed is smaller. Like this. So because upstairs 2a is constant, when r is bigger, theta dot decreases. This is exactly this picture. Alright, so you can substitute theta dot back into 1. Sub into 1. Sub into 1, what do you get? So you get r double dot minus r times theta dot squared, which is 2a squared. Actually, yeah, it would be 4a squared, 2a quantity squared, and then over r what? R cubed equals 0. This is still tricky. I mean, it's still nonlinear. Can we do something about that? Oh, this way you just get r double dot minus 4a squared over r squared equals 0. Can we solve this? What does it feel like? This feels like, this feels like the equation of motion under gravity, huh? Because it's like, or some kind of inverse square law. R double dot feels like acceleration, right? 4a squared over r squared feels like a force that satisfies the inverse square law. Is there a nice solution for that? I don't think so. I don't think so. Actually, I did, like way earlier, like over a year ago, I did a video on calculating the time, the falling time, okay, of an object from a great height. Right, that would be pretty much the exact same problem. It's a differential equation. The force is a nonlinear term like this. You can't solve it. You can't solve it, but it's nasty, man. It's nasty. You can solve it, but it's nasty. But leaving this aside, I just want to give the brief idea of how to actually solve this, because this is a second order differential equation in which the first order derivative is absent. You can use a substitution to do this. It's equivalent of energy conservation. It's equivalent of energy conservation, and here is how it works. So you can, hold on, you can do this. You can say r double dot equals 4a squared over 2 squared over r squared. You can do a little trickery, so multiply r dot. So multiply r dot, and this feels like such a random option, but this actually makes sense, because this is how you derive the work energy theorem in mechanics. So just to give an extra motivation, because F equals ma, right? Let's just take in a one-dimensional case to simplify stuff. So what you do is you actually do this. This is mv dot. This is mv dot. Okay, you actually multiply v on both sides, so fv equals mvv dot. But what is vv dot? Well, that's just half mv squared d over dt. That's the time derivative of half mv squared. And this is where the kinetic energy comes from the power rule, half mv squared d over dt. So there's that, and you want to integrate this. You get the integration of fv dt integral equals the change delta in the change of half mv squared. And what's this? Well, v dt is just ds, so this is the work integral of f ds. This is work. But it's the same trick. You multiply v on both sides. So here I'm multiplying r dot on both sides. Just stripped of its physical meaning. Same trick. All right. So let's do that, and you get r dot. You get r dot, r double dot, r dot, r double dot, and then it equals what? Equals 4a squared, which is a constant, and then r dot, r squared. Can we see something going on both sides? On the left, you got d over dt of half r dot squared, right? Just like in the kinetic energy. Like this looks like a kinetic energy, right? Half speed squared. This is half r dot squared. There you go. It's on the left, and on the right, what's that? Right on the right, you use the chain rule. So you get d over dt of 4a squared times what? Times, this is minus 1 over r. there's that. So this way you found another integral of the motion. This way you found another integral of the motion. Let me just double check. Yeah, it looks about right. So what this says is d over dt of half r dot squared plus 4a squared over r equals 0. So basically, this has to be constant. So therefore, let's call that b, shall we? We got half r dot squared plus 4a squared over r equals b. Equals b. Okay. And after that, so now essentially you have a 1D, or sorry, a 1, what's that called? So now you essentially have a first order system. So we reduced the original second order equation to a first order equation. Right. So there's that. This is basically energy conservation in mechanics. Equivalent, mathematical equivalent. So now we need to integrate that, which is a bit of a pain. Actually, you know what? Can I eliminate, say, I just want a relationship between r and theta, right? Because this is the parametric form. The parametric form here is, by the way, just to recall, the parametric form uses the arc length parameter. It uses the arc length parameter, which may not be the most inconvenience in the world. Because in general, arc length can be very difficult to calculate. So that's what it's saying. Like, can we somehow eliminate the middleman, the middle parameter, and just get a differential equation for r and theta? Can we do that? If so, that would be great. That would be awesome. I really wanted to eliminate the middle parameter because in principle you can't integrate this, right? It is possible to integrate this. So you can write r dot, can isolate r dot. R dot would be, well, 2b minus 8a squared over r, and then taking the square root, plus or minus. You can save the plus or minus, but yeah, save the plus or minus, and basically this is dr over the square root, and you just have a nasty integral to solve. A squared over r, and you get a plus or minus ds. This is arc length parameterization. I stress that again. This is arc length parameterization, so it's not dt but ds. And you just integrate this. This is possible, and I showed it in one of my earlier videos, but it's not fun. All right. So, I mean, at this point, I guess I just want to move on to the next example. The physical explanation that acceleration equals 0, and hence it's a straight line, is meaningful. However, to derive it, to actually solve the differential equation is a bit of a pain. Okay. So let's just put it that way. All right. So, chat, any comments? Any particular thoughts on this process? I mean, I know this is perhaps. I mean, I'm just doing derivations on my own, like talking to myself most of the time, because this is what this series is about, like prepping and reviewing, and we'll try to find a more examples to this theory. Okay, so anyway, I'm going to move away from this example, okay, and I'm going to do the second example, that is just a unit sphere. So, what would be the geodesic on a unit sphere? Right? Just use our everyday common sense. Unit sphere. So let's use a unit sphere. So I'm going to be using the latitude and longitude parameterization. unit sphere. Okay, we have a nice picture situated in the 3D space. Although that's irrelevant. I mean, we're gonna eventually discard the 3D space and think of the sphere on its own. We're doing geometry from the perspective of its inhabitant. All right. So here, this is a unit sphere. Let's just pick an arbitrary point and think about how do you parameterize it. Well, let's use the geographic parameterization, longitude and latitude. Seems pretty natural. So it works like this. So imagine if this is the meridian for 0 longitude, and let's call the longitude what would be the right angle. Let's call that phi. Okay, phi is the longitude like this, and the latitude, let's call that lambda. Is lambda. Okay, so this is a point on the sphere, and of course you can write x, y, and z in terms of these two angles. All right, so it's just a standard spherical coordinate transformation. So okay, x, the radius is r, by the way, because it's a unit sphere. So x would be, actually z would be easier. Z is, from the picture, is just use a trig relation, it's just sine of lambda. Okay, this is x, and y would be what? X would be the cosine of lambda times the cosine of phi. This would be x, and y would be cosine of lambda times the sine of phi. Okay, so this is a unit sphere parameterization. Okay, so what do we want here? We want the metric tensor and we want the geodesics. Okay, and of course we need a Christoffel symbol in the process. Let's do the calculations. And before we do that, what do we imagine? What do we expect? Okay, what do we expect here? The geodesics should be, great circles. Should be great circles. So let's draw a picture. So great circle is just a circle obtained by cutting the unit sphere through its center by a plane. So that's a great circle. So the cross section would be a great circle. The geodesic on a unit sphere should be a great circle, or at least an arc of great circle. Let's draw a picture. So this is a simplified picture, all right? So let's say you got 2 points on the sphere. So the shortest distance between the two is given by an arc that is part of the great circle on which the 2 points lies. Imagine here, this is the 2 points of interest. Let's say you want to get from New York to London in the shortest geographical distance. So what do? Well, you connect. Sorry, you look at the points. Okay, the points in space, New York, London, and the Earth center. So the 2 points dictates a plane, and you just draw that plane, and we'll cut the Earth, intersect the Earth, and the cross section will be a great circle. And you just pick the shorter arc on that great circle from New York to London, and that will be the geodesic. And that's our intuition. So we hope to be able to recover that. Although the annoying thing is that even though the geometric intuition is clear, just like in the previous case, right? In the previous case we've been working on the 2D plane. Geodesic should be straight line. This is intuitive. However, even after you derive the geodesic equation, it's not that obvious that this is a straight line. We have to do this, we have to appeal to physical argument. arc acceleration equals 0, okay, therefore by the Newton's first law, you get a straight line. I was trying to get a mathematical justification, but the integral is just too nasty. Okay, so I don't know, like if let's say I wanted to confirm this geometric fact, right? So the geodesics should be great circles, but because of the previous example, I don't know, like if we derive the differential equation, say satisfied by lambda and theta, it's unlikely. I mean, I wouldn't say it's unlikely, but there's a good chance that the solution, not the solution, but the differential equation itself wouldn't be so obvious. Okay, wouldn't be terribly obvious that, oh, this is a great circle. Perhaps we have to look at special cases to get our answers, which is annoying, but I don't know. We just do our best, I guess. This is the geodesic, which are great circles. It's supposed to be that case, but let's just see what the calculation gives us. So what do we do at first? We need the metric tensor. Right? We need the metric tensor, so we need, and how do we derive that? Right. This derivation here is not completely useless, by the way, because this tells us how do you derive the metric tensor. And now we can use the same method here. So the line element on the sphere is dx squared. So ds squared is dx squared plus dy squared plus dz squared. So starting from this one, the background helper Cartesian coordinate. And then let's just calculate ds, dx, dy, dz, right? Treating this as total differentials. So dx would be, well, partial derivative dx over d lambda, total differential d lambda, plus the partial derivative dx over d phi times d phi. So let's do that, and you get minus sine of lambda, minus sine of lambda cosine of phi d lambda plus dx over d phi. That would be minus cosine of lambda sine of phi, and then d phi. All right. So this is dx, and you get dy. dy would be dy over d lambda plus dy over d phi, dy over d phi, and then times d phi. All right, cool. And do the differentiation, you get minus sine of lambda, sine of phi, minus sine of lambda, sine of phi, and then d lambda plus dy d phi, which is positive cosine lambda cosine of phi, and then d phi. All right, and lastly dz. Well, dz is just dependent on the sine of, that's just dependent on lambda, so it would just be this will be easy. So this is just cosine of lambda d lambda. All right, and now let's calculate the sum of squares. So you got ds squared. So this thing is squared. Let's do that. Here you go. This thing squared, and then plus this thing squared, and finally plus cosine lambda d lambda. So simplifying this should give us the metric tensor on the sphere. And now you can, and after that, you can treat the metric tensor on it as an intrinsic object. All right, so here, there we go. You got the first term squared plus the second term squared, and then plus the third term squared. Okay, and just do the calculation carefully. So here we have sine square lambda cosine, sine square lambda cosine square phi d lambda squared plus 2 sine lambda cosine phi cosine lambda sine of phi d lambda d phi. And finally, cosine square lambda sine square lambda d phi squared. And then plus, that's the first line. The second line would be sine square, let me just put the bracket here just to demarcate these terms. So we got sine square lambda sine square phi d lambda squared plus, actually minus, opposite sign, because 2 sine lambda sine of phi cosine of lambda cosine of phi d lambda d phi. And lastly, the last square term in the ds squared would be cosine square lambda cosine square phi d phi squared. And lastly, you got the last term, which is cosine square of phi, cosine square lambda, and then d lambda squared. Okay, so what's the coefficient of d lambda squared? You got sine squared cosine square phi plus sine square lambda sine square of phi. So these two terms just combines to sine square of lambda. And because of the last term, which is cosine square lambda, you just get d lambda squared. Okay, that's pretty nice. This is d lambda squared. And notice that how the cross term vanishes. Right? It does. Sine of lambda is the same. Sine of phi, cosine of lambda, cosine of phi, cosine of phi. So they cancel. There's no cross term, which is fantastic. Even though this looks horrible, but actually it's pretty nice. And now what's after? Well, what's after? It seems like you got cosine square lambda as a common factor. Right? And then you got sine square lambda plus cosine square lambda is 1. So this is just cosine square of phi d phi. D phi square. So this is ds squared. And therefore, let's conclude that this is a line element expression. Okay, box that and say, this is a line element on the sphere. Let's think about it. Does it make sense? Line element on the unit sphere. And now, from this point, you can forget about the Cartesian coordinate and just work with this. Right? So now you're totally from the perspective of an inhabitant of the sphere. So here we're looking at Earth from the perspective of an astronaut. Okay? So imagine X, Y, Z are 3 distant stars, and you create this coordinate system and see, oh, this point on the sphere of the Earth has coordinate x, y, z. But that's not what we really care about, right? We care about the geometry from the perspective of inhabitant of Earth. So on Earth, you need 2 coordinates, lambda and phi, and what we just derived is a line element on the unit sphere. So does this make sense? Think about it. Does it make sense? Well, d lambda, what's d lambda? So imagine taking a side view. Imagine taking a side view on the plane on which this right triangle is located. All right. So let's take a look at the picture here. You got this circle, and we're looking at from the side. Okay. So this is the angle, lambda, the latitude. This is lambda, the latitude. All right. So imagine if you change lambda by a little bit, like this. So this is your d lambda. Okay, because the radius is 1, the arc length traversed is approximately d lambda. So that's one perspective. Okay, and now let's consider if you fix lambda but changes phi. If you fix lambda but you changes phi, how does say the distance or what kind of infinitesimal distance does it traverse on the sphere? Okay, we need another 3D picture here. Let me just zoom in a little bit. All right, so this is a sphere, and we're going to draw the 3D perspective. So that's the equator, and then you got the x, y, z axes. Actually, you know what? We don't need that, do we? Okay, let's forget about the x, y, z axes actually. So, but instead, I need a reference direction to say this is my phi. This is my phi, and now imagine if you change. Actually, you know what? You got to keep lambda constant. So we need the vertical axis as well. So let's say this is constant lambda. Constant lambda. All right. So I'm gonna draw a meridian that corresponds to this particular latitude phi. This is the latitude. Sorry, this is a meridian. Okay, that corresponds to the longitude phi, like so. And then I'm just going to change phi by a tiny amount. And that can be, of course, be labeled as this particular arc, this piece of arc. It will be d phi. The length of that will be d phi. So the meridian is now rotated to this new location. The meridian is now located to the new location. However, because lambda is fixed, right? Lambda is fixed, as you can tell from the diagram that at the fixed lambda, at the fixed latitude, here, this is the fixed latitude. This is the constant latitude line. Okay, this particular piece of arc would be what? Would be what? Well, this is exactly cosine of phi. This would be actually cosine of lambda, I believe. This would be cosine of lambda. Actually, you know what, guys? I think I made a mistake here. Yeah, cosine of lambda. Oh, this is a mistake. This is the first term expansion is a mistake there. First term expansion should be sine of phi. Sine square of phi, that's why. Yeah, there's a mistake. I'm glad I was able to caught it. Yeah, so you should always do a sanity check. This should be cosine of phi. Cosine of lambda, my bad. Okay, the idea is that if you're in a, say, high latitude region, so if you're, say, high latitude region, when you rotate, when you increase phi, when you increase the longitude, the radius of the the radius of the red circle decreases. On the North Pole, that's exactly 0. And what is cosine of lambda? By the way, this is not cosine of lambda, but rather cosine of lambda d phi. Cosine of lambda is this radius here. Look at the picture. This is cosine of lambda. So when phi changes, it creates this new meridian which intersect with the red circle. And the arc, this little piece of arc that's created in the process that's shown here, is cosine of lambda times d phi. So that's the meaning of this expression. Right? So on the surface of the Earth, right, you either change your longitude or change your latitude. Change in the longitude creates this contribution in the line element, whereas changes the change the latitude creates this contribution in the line element, changes the longitude, creates this next term. However, this contribution is scaled according to the position, like how north or south you are. Okay, on the equator, changing the longitude creates the largest possible resulting line element. Whereas if you're on the North Pole or the South Pole, changing the longitude does nothing. Okay, so that's the intuition of this formula. And now we're going to rewrite this as a metric tensor. So you now have the line element, so you have the metric tensor, same thing. So the metric tensor, let's call it Gij, just like earlier, is also 2 by 2 matrix because you got 2 coordinates, which will be 1, 0, 0 cosine squared lambda. You see, now we don't need to worry about the Cartesian coordinate system. You can just treat this as a fundamental object. And Gij would be, the inverse matrix would be 1, 0, 0, secant square of lambda. Secant square of lambda. Okay, so that's the inverse or the contravariant reciprocal metric tensor, whatever way you want to call it. Okay. And now we can calculate, what's that? Calculate the Christoffel symbol. Boom. Christoffel symbol, do it all over again. There are 8 numbers here. The Christoffel symbol. And then we'll substitute the Christoffel symbol into the geodesic equation. And even though if you can write down the geodesic equation, but solving it may still be a problem, as I mentioned earlier. But let's just see how that turns out. Okay. Anyway, so this is a formula for the Christoffel symbol. So here let's denote x1, x2 as already committed. So lambda is 1. Already committed based on how we write the metric tensor. So the first position is the coefficient of d lambda squared. So x1 is lambda and x2 is phi. You already committed here. All right, guys, I just need to use the bathroom real quick. I'll be back. Okay, I am back. Okay, let's now calculate the Christoffel symbol on the unit sphere under our parameterization. Longitude, actually, it's latitude, longitude, latitude, longitude. Okay, parameterization. So the first equation should be gamma. So actually, let's fix 1 on top. Gamma 1, 1, 1. To 8 of them, as earlier. Gamma 1, 1, 2. Gamma 1, 2, 1. Gamma 1, 2, 2. All right, let's continue. We got gamma 2, 1, 1. Gamma 2, 1, 2. gamma 2, 2, 1, and gamma 2, 2, 2. Okay. So gamma 1, this is G1 sigma over 2 times dg over dx plus dg over dx. I'll worry about the indices in a second, dg over dx. All right, so you have, say, 1, 1 for the last g, and its x has this sigma attached to it. G sigma, sigma, 1, 1, 1, 1. Okay. Okay, so, well, g is still diagonal, so there's only one term in the summation. It's the summation with two terms. So you got g11 over 2. Continue. You got dg11 over dx1. dx1 would just be d lambda plus dg11 over, once again, d lambda. And then minus dg11 over d lambda. This is 0 because g11 is a constant. Okay. So at this point, we can just be lazy and just write, here you have g 1. Once again, you just need g11. g12 wouldn't be needed, so g11 over 2 dg over d something plus dg over d something, and then minus dg over d something. Okay, so do this again. 1, 2 here, and the only summation index that gives us a non-zero contribution is 1. So this is dx1 again. So dx1 would be dr, d lambda, okay? And the summation index is 1, so you got a 1 here and a 1 here. And because you got a 1 here, so this is 1, this is 2. And the first term should be dg11 over dx2, but x2 is phi, so that's d phi, and this is d lambda. Okay, the expression is now completed. Okay, so let's continue here. Well, g22 is 0. G12 is 0, G12 is 0, so the last two term cancels. G11 is a constant, so that's 0. So this is just 0. Okay. Let's continue. Big gamma 1, 2, 1. Big gamma 1, 2, 1 would be G 1, 1. Yeah, once again, because of 1 on top. G11 over 2. dg something plus dg something minus dg something. Okay. The last one is dg12 over dx1 because of the 1 here in the summation index, and x1 is lambda, so it's dg21 lambda, like this. Okay. So as I mentioned, the summation index is 1, so you put a 1 here, 1 here, 2 here, 1 here. Okay. So the first term would be dg12 over dx1. dx1 would be just d lambda, so put a lambda here. And dg11 over dx2, and x2 is phi, so this is phi. Alright, so everything inside the bracket vanishes, either because of g12 is 0 or because g11 is a constant, so this is 0. Nothing. Okay, so next up, the gamma 1, 2, 2, alright, so g11 over 2 dgd something plus dgd something minus dgd something. Alright, so here the last g is g22 over dx1, so it's over d lambda 1, 2, 1, 2. Okay, so it should be dg12 over dx2, which is d phi, and this is d phi. All right, so finally a non-zero term, because G22 is cosine. Actually, sorry, this is terrible. This should be, oh no, nothing is wrong. It's actually square. You actually do need square. I was thinking, oh, do I need to remove the square here? No, you keep the square. If you remove the square, then the quadratic form fails to be what's that? Fails to be a positive definite. You need the square here. Okay, so well, just differentiate cos square. You get 2 times cosine squared times minus sine of lambda. Okay, so there's that. Okay, so here you got G11, as I said, is 1 over 2 times minus, there's a minus sign. Should we get rid of that? Probably, because cosine squared has derivative of 2 times cosine times minus sine. So you just get 2 times cosine times sine. This is a cosine of lambda, sine lambda. That's the Christoffel symbol when the upper index is 1. Now let's do the other 4. Okay. G2. Okay, G2. So you need a 2 on top because of this symbol. But once again, because G is symmetric, only 2 matters here. Only sigma is 2 matters here. Okay, so now you have dg over d something plus dg over d something minus dg over d something. Okay, and so, well, you got a 1, 1 at the end, and the summation index is taken to be 2, so dx2, which means you got to differentiate with respect to phi. So 2 should be present in the first 2 g's, and you got 1 over dx1, which is d lambda, and 1, the second term is also dg21 over d lambda again. Okay, this is 0, either because the off-diagonal terms g21 is 0 and g11 is a constant. So this 0. All right, so the next term would be half of g22 dg something over dg something minus dg over d something. Okay. Okay. So there's that. Here still it should be should put phi here and 1 2. So this completes the last term. And on top you got g2 2. Okay, 1 over dx2 would be phi, d phi, and the second term dg21 over, actually, sorry, dg, no, that's actually not right, my bad. The second term is dg22 over dx1, which is lambda. Okay. Okay, so I think we'll finally have a, yeah, this one is also non-zero because of this thing. Okay, so half g22 is once again 1/2. Remember, g upper 22, oh, actually, my bad, g upper 22 is not 1/2, is here. It should be g22 is upper g22 is secant square. Secant squared lambda here, and the two off-diagonal terms cancels, and minus here dg22 over d lambda, we calculate that, right? So that's 2 times cosine of lambda sine of lambda. Okay, so 2 cancels, and one of the secant, actually minus, I forgot the minus. So it should be minus cosine, and one of the secant cancels, and secant times sine would be sine over cosine, which is tangent. This is minus tangent lambda. Okay, next up. So this is g22 over 2 dg over d something plus dg over d something minus dg over d something. So first of all, because of the summation index is 2, you have dg over d phi in the last term. And for the last term, g should be attached with a 2, 1. Okay, so 2, 2, 2, 1. Okay, the first term is dg22 over dx1, which is dg22 over d lambda. And second one would be dg21 over dx2, yeah, which is phi. All right, so you still have one non-zero term. So g22 on top would be would be secant squared of lambda over 2, and dg22 over d lambda would be 2 times cosine of lambda minus sine of lambda. Oh, sorry, minus sine of x. This is the same as the previous term. So this is minus tangent of lambda. Okay, minus tangent of lambda. So we have that. Okay. Well, the last term would be g22 over 2 dg over d something plus dg over d something minus dg over d something. In this case, it would be dg22 over d x2. X2 is just x2 is just phi. Okay, and earlier you have just 2 everywhere. 2 everywhere, so this is phi again and phi again. And the last term just vanished. Okay, so these are the 8 Christoffel symbols done. Okay, and now we have the geodesic equation. So these 2 examples should make it pretty clear of how to apply this recipe, even though solving the geodesic equation is not a simple matter. Okay, so setting it up is relatively straightforward. Okay, so you have x1 dot. We'll convert back to original coordinate name later. So you got x1 double dot plus gamma 1 alpha beta x dot alpha x dot beta equals 0. And the second equation would be x double dot 2 plus big gamma 2 alpha beta x dot alpha x dot beta equals 0. All right, so, well, what is big gamma 1 alpha beta? Only one term is non-zero, the third term. Actually, the fourth term. So this is just x double dot 1 plus gamma 1 2 2 x dot 2 equals 0. Okay, and the second equation would be x double dot 2 plus, well, there are 2 terms here. You got gamma 2 1 2 x dot 1 x dot 2 plus gamma 2 2 1 x dot 2 plus x, not plus, but times x dot 1. Okay. Convert this back to the equation. Convert this back to the notation of original coordinate. Okay. And this is the same as lambda double dot plus, here, what's that? We got cosine of lambda, sine of lambda, x double dot squared, which is what? x2 double dot. x2 double dot would be, hang on, x2 double dot. Sorry, it'll be phi dot squared. Okay, sorry, I'm yarning. Okay, and the last equation would be x double dot 2 would be phi double dot. Right? That's phi double dot here. And then plus, this is 2. There should be a 2 here. And minus 2 tangent of lambda. And then lambda dot times phi dot. See, once again, I don't have a good way to solve this. So that's the geodesic equation. Although, I mean, I want to have some way to verify this is actually the great circle. So perhaps, just perhaps, we can write down the equation for the great circles. What will be a general great circle on the line, on the sphere? And then differentiate and see if it satisfies this equation, I suppose. What would be the general equation of a sorry, not a geodesic, but rather a great circle? Equation of a great circle on the sphere. Is there either way to represent that? I mean, it can be slanted in general, right? The great circle, it doesn't have to be like this. It can be slanted. So that's tricky, huh? Because the great circle is defined as the intersection of a plane through the origin and the circle. So it's rather unsatisfying if we can't verify that this actually corresponds to a great circle. Yeah, sorry guys. Okay, I think I'm gonna leave this, okay, and just put a question mark. Maybe I'll come back to this. How to check a great circle satisfies this, or even better, solve the equation of the great circle from this differential equation. But this is highly nonlinear. These are great circles. Not easy. Not easy at all. Okay. So at this point, I think we're ready to move on with the next new material. That is the law of transformation of the Christoffel symbol. And we will finish deriving that and we'll call it a day. The law of transformation of the Christoffel symbol. And this explains why the Christoffel symbol is not a tensor. Law of transformation for the Christoffel symbol. Okay. All right. So recall that the geodesic equation is given by the following. D squared xi over ds squared plus gamma ijk and then xj over ds times dxk over ds. So this is a geodesic ODE. Okay, this is a geodesic ODE, and of course here this is using the coordinate system. The coordinate system x1 all the way to xn. Okay. What about new coordinate? This is our new coordinate. The law of transformation is all about how do a set of array, a multi-dimensional array behave under a new coordinate system. So we want to connect these two. So the new coordinate system would be x1 bar all the way to xm bar, right? So this is our convention, starting all the way from the beginning. The bar coordinates are the new ones. Okay, so of course this is still the geodesic. Right? Geodesic is something that is intrinsic to the Riemannian space in question. All right, so this would be d squared x bar I over ds squared. So the format is exactly the same. And now the big gamma will also take on a bar. This is the new Christoffel symbol. So our goal is to relate the new and old Christoffel symbol. So you have these two equations. Both are geodesic equations, one in the old coordinate system, one in the new coordinate system. And of course they should represent the same kind of object. Okay. We now find a relationship between big gamma ijk and big gamma bar ijk. So can we get a relation between the two? Well, let's just use chain rule, shall we? Because by the chain rule, you got dx, ordinary derivative. By chain rule, dx bar j over ds is actually partial derivative, dx bar j over dx alpha unbarred, and then ordinary derivative dx alpha over ds. So you got that. And what about the second derivative? Well, the second derivative is awkward because you need to use a product rule here. Because you see, when you differentiate this once again by the chain rule and product rule, to find the derivative of second order derivative, you need the product rule. And that messes up the transformation law. Remember earlier when we derived the when we derived the transformation law for covariant and contravariant tensors, all we needed was the chain rule and no product rule. What's so great about not needing the product rule is that you don't need the derivative of the Jacobian itself, but here it is now unavoidable. So differentiate this one more time. You got, just write things slowly, okay? So you got d over d squared over dx bar j over ds squared. Okay? This is d over ds of this thing. Okay, so what does that mean? What does that mean? Well, remember here, you already have a summation implicitly going on. Let's just differentiate this. Okay, so the first term, you also need a product rule. Not a product, sorry. For the first term, you need another chain rule. So you need the second derivative. This is the second derivative, d squared x bar j. Okay, d squared x bar j over, you get dx alpha here, and you need a dx beta up front, and then times dx beta over ds. So this is just chain rule applied to this factor. And then times dx alpha over ds plus, well, that's the product rule. Well, let's just get the x bar j over dx alpha times dx to the alpha over ds squared. Like this. Oh, sorry, my bad. It should be second derivative, not squared. This makes no sense. This should be the second derivative. You're differentiating this factor here. This is d squared x to the alpha, not x to the alpha, but just d squared x alpha over ds squared. So you see, you love this kind of stream. Math is addictive, and I mean a lower level of it. Yeah, math is beautiful. Is just it takes a lot of time and effort, and it's not the easiest thing to do. But if you're motivated, you can't stop doing it. You literally can't stop doing math. It's addictive in that sense. Even though you get constantly frustrated and you still can't stop doing it. It's just you want to know what is going on. You want to understand the mystery. Right? So here, okay, think about the meaning of the second derivative. The second derivative term, it means that the Jacobian is non-constant. If this is non-zero, okay, if this is non-zero, then the Jacobian will be, if the Jacobian, I'm trying to say, if the second derivative is non-zero, it means the Jacobian is not the same from point to point. I'm about to go to multivariable calculus, a bit scared, but Calc 2 was easy, so I think Calc 3 might be, actually, no, you know what, Calc 3 is actually much harder. I mean, assuming you're in North America, Calc 2 is still single variable stuff. So going from Calc 2 to Calc 3 is actually a big jump. Multivariable stuff is significantly harder than single variable stuff. Okay, and you can think of what we're doing here is Calc 3 on steroid. So tensor calculus is really the natural next step for multivariable calculus. Okay, because vectors aren't enough. Okay, vectors aren't enough for physics, engineering anymore. So you have to. This is basically. By the way, we've been invoking things like the chain rule repeatedly. This is the multivariable version of the chain rule. The W ideal is multidimensional. I'll be in my code. I'll be good. Okay, I don't know what that means, but well, math is not code. Math is code is just a way that you can do calculation in an automatic way, right? So your understanding is independent of code. Like I use vectors. Yeah, I mean I was talking about vectors, but what we're doing here is because vectors aren't enough anymore. Not even matrices are enough. So you need this kind of crazy-looking 3-index array called Christoffel symbol. So let's continue. Yeah. So basically, because of the second derivative doesn't behave like a tensor. So you see, second derivative isn't a tensor already. This isn't a vector. This isn't a vector. This is a vector. This is a vector. So here, the first derivative, that's the tangent vector. That's a tangent vector. And actually, we introduced the law of transformation for covariant vectors using the tangent vector. This is a tangent vector, and this is a contravariant tensor. This is a contravariant tensor of rank 1, aka contravariant vector. But this thing is not. If it is, then this term would go away. This is not a tensor. If this were a tensor, then only should the last term remain. But that would mean the coordinate transformation is affine. The coordinate transformation is affine. The transformation matrix, the Jacobian is constant everywhere. but that's not guaranteed. You can have a curvilinear coordinate system and this term will not vanish. So the bottom line is the tangent vector is a tensor. Like speed is a tensor, sorry, not speed, but the velocity is a tensor, but acceleration isn't. Acceleration isn't. It sounds a little bit odd, isn't it? Acceleration isn't. Because of this thing. Okay. Anyway, let's continue. So what are we trying to do here, right? So we're going to substitute these into the second equation. So let's call this 1 and 2. And compare with 1. Substituting these into 2 and compare with 1. Substitute into 2, so the first term would be this thing. This is the second derivative. There you go. All right. And here is the new gamma, which is what we wanted. All right. So the new first order derivatives are as follows. This term here is this. And the second term, you just swap k to j. That will be done. All right, so let's erase that. All right, so you have this one. Okay, just to make things easier to spot, next time we read it, we're going to label everything. Okay, swap the k, j to k, like this. All right, so this one is dx bar k over ds. This is dx bar j over ds. All right, so yeah, this one right here is the second derivative. d square x bar j over ds squared. Right, just do a quick sanity check, and alpha beta should be dummy indices. Yes, there's dummy index here, dummy index here. Okay, now, excellent. So after the substitution, let's compare that with 1, shall we? Let's compare that with 1. So 1 is what? 1 is this thing. 1 is this thing. So this is a mess. This is a mess. So what do we need? Well, we need the d squared I. We need d squared I over ds squared. So we need this thing to be isolated. So to do that, we need to multiply both sides by so essentially you want to create a Kronecker delta. That's what you wanted. So you want to calculate, multiply by the inverse matrix. Actually, before we're doing that, let's just do a rearrangement first. Okay, so this term, let's put that as the first one. What we really care about is this thing. So eventually we're going to get rid of the Jacobian factor here. And here we have how do we handle the two terms here? Actually, you know what, guys? I'm going to multiply by the Jacobian matrix right now. So multiply by the inverse Jacobian. So considering the fact that I wanted something like this. So I want dx squared I, for example. What should I do? So let's multiplying dxi over dx bar j. Consider multiplying this on both sides. And the advantage of doing that is that it gives us the d squared I over ds squared. Because doing so, because dxi over dx bar j times dx bar j over dx alpha times d squared x alpha over ds squared now can be simplified. All right, so the first two together would just be the Kronecker delta. This is the inverse matrix after all, so this is a Kronecker delta I alpha, and then times d squared x alpha over ds squared. So swap the index and you get d squared I over, no, d squared xi over dx squared, which is exactly what we wanted. We want this thing, d squared xi over ds squared, so we want that. So let's do so. All right, so multiplying that, you get the first term now pops out to be just d squared xi over ds squared, and then plus, remember, what's the factor here? Well, you got dxij over ds, dxk over ds, right? So we want that as well. So we can do that by factoring out just dx alpha over ds, dx beta over ds, with this second order term, the second order derivative, just right here, multiply by this thing, multiplied by this thing. Yeah. Okay, so this makes sense. And then plus big gamma bar ijk, big gamma bar ijk, and you have yeah, this thing. Hold on. Yeah, we multiplied this on both sides. And here you have the dx bar over, I think this will be, this will have some kind of cancellation as well. This one and this one. Okay. Now just double check to see everything still makes sense, because there's a lot of symbols. Okay, so I isolated the first term because I want that, and I isolated the product of the first derivative dx alpha over ds, dx beta over ds, so that's what I wanted. Okay, and then I just multiply the second derivative with the inverse Jacobian, and here the big gamma bar, we need that. We got two Jacobians, j over alpha, k over alpha. Hold on a second. Why do we have j over alpha and beta? That's bad notation. That's terrible notation. Alpha appeared 4 times. We don't like that, so let's put a beta here instead. Okay, so that's not very good. Oh, that's the cat. cat is getting hungry. Okay, so beta, let me change that. Okay, so this is what we wanted, and put a beta here. Yeah, dx bar over x beta. Okay, okay, this is cool. Did I? Oh, sorry. I mean to put a beta here. Yeah, beta here. Okay, and now let's compare this. And now let's compare with, hang on a second. Hang on a second, what's going on? Compare this with 1. This is 1. This is 1. So what should happen here? Oh, compare with 1, so, well, you can change the dummy indices j and k to alpha beta. That shouldn't do any harm. So this is alpha. Let k be beta. Compare with 1. All right. This is the equivalent form. So you get the relationship, basically. So this way, you see this giant coefficient should be the same as this one. And in particular here, we notice there's another Kronecker delta going on. Okay, that's another Kronecker delta. Okay, so pay attention that this is another Kronecker delta. This is just delta I alpha. Which means you can swap I here to alpha. Amazing. Amazing, isn't it? So you can do that. So yeah, let me just wrap this up real quick. So here so far this is what we have. We want to have the old, what's that? We want the new Christoffel symbol to be in terms of the old Christoffel symbol. Okay, or I mean you can't do the other way around. I think that's also fine. I think that's also fine. But did I mess up here? Did I mess up? I think I might have messed up somewhere. I think I have messed up somewhere. Because it doesn't look like what the textbook says. All right, so let's think about what is happening. I multiplied this on both sides, and then you have what? And then you have after substitution, got this gamma with the four derivatives at the end, right? And by taking out the common factors, which is dx alpha over ds and dx beta over ds. Yeah, that looks great. Second derivative. Oh, actually, Actually, I've done mess up. Did I do mess up here? Because here in the original I is a free index. Yeah, this is another index problem, isn't it? Yeah, this is a problem because here I should have used I should have used I, okay? So here I should have used I because of this I. Let me just change that, okay? When you do tensor calculus, be very mindful which indices are already used as free index. And this is what happens when you stop paying attention. I mean, and these small mistakes can create big confusion later on. So this should be I. So there's got to be some changes down here. I. So I is a free index. I is a free index. So yeah, this should be I. Oops. This should be I. Okay. So other than that, so far this step is fine. But because I is a free index, you can't use dxi. You have to use something else. So let's use dx, say, sigma, and then put dx bar I at the bottom. Okay, this way you can isolate d square x alpha over ds squared. Okay, so let's do that. Here, dx alpha over dxi. Dx alpha over dxi times dx bar I over dx alpha. Actually, that's not a good idea either, is it? Oh, right, I mean sigma, not alpha. Alpha is a dummy index, so that can't be used either. So this should be sigma. Sigma, okay, xi, and this should be sigma. Sigma, okay? So the first two terms combines to delta sigma alpha. Delta sigma alpha, and swapping alpha gives you d squared sigma over ds squared. Okay. Okay, so this is fine now. And let's see what needs to be changed. So we're multiplying this equation by dx sigma over dx bar I on both sides. So the term now isolated should be d squared x sigma. Yes, d squared x sigma, like this, d squared x sigma over ds squared. Over ds squared, and now let's see, what are the terms factorizable? Well, you got dx alpha over ds, dx beta over ds, that's correct. And here, the second derivative needs to be changed. It's d squared x bar I, yeah, d squared x bar I here. And the Jacobian is now dx sigma over dx bar I. Sigma up, I down. Sigma up, I down. Okay, that's cool. And the last term, we got big gamma, ijk. And what else? Here, yeah, this is okay. This is okay. dx bar, dxj bar, yeah, dxj bar, dxj bar over dx alpha, yes, dxj bar over dx alpha, dxk bar over dx beta times dx sigma. Yeah, so this is why the confusion became okay. So this should be dx sigma over dxi. So there's no Kronecker delta here. There's no Kronecker delta. Be very careful about indices. Just try to keep like I would rather actually I think I'll do this starting doing this next time, because later on we'll be dealing with curvature tensor. There's so many indices. There's so many goddamn indices. You gotta keep in mind of which ones are already used, which is the free ones, which are the dummy ones. Just make a list on the side, and whenever a change happens, change on the side. All right. So here you multiply dx sigma over dxi. So no contraction can happen here. See, all indices are unchangeable. So basically now you're pretty much done, right? Yeah. So pretty much now you're pretty much done. So that's the old. Hang on. That's the old Christoffel symbol in terms of the new Christoffel symbol. So it is now absolutely crystal clear that Christoffel symbol is not a tensor. If it were a tensor, then the first term would be 0, which there is no guarantee. Okay, so this is the transformation law. The transformation law satisfies the Christoffel symbol. Because of the first term, without the first term, it would be a tensor. So, yeah, there's that. Okay, so the final comment is that the Christoffel symbol are not components of a tensor, so that the Christoffel symbol might be 0 in one coordinate system, but not in all coordinate systems. Right? So this is a different feature compared to tensors. Remember, what's tensor? Here. If a tensor is identically 0 in one coordinate system, it must be identically 0 in all coordinate systems. It's just because here, imagine t is 0 here for every possible indices, then it doesn't matter what your coordinate transformation is, the tensor is always 0. But here, if you have a Christoffel symbol that is identically 0 everywhere, you can get a non-zero Christoffel symbol, and that's exactly the case. Yesterday, when doing our very first example, in a Euclidean space with Cartesian coordinate, right, gamma is everywhere 0. But, well, we just did the polar coordinate today. We're still dealing with the same space. Here, we're still dealing with the same space, but because of Christoffel symbol isn't a tensor, you can get non-zero entries. So this is an excellent illustration. Okay, so that'll be it for today. So today we've seen more examples of the Christoffel symbol as well as geodesic. A main takeaway is that even though sometimes the geometric interpretation of the geodesic is clear, the geodesic equation don't always immediately lead to that conclusion. So it might be still special tricks needed to solve for the geodesic equation, which is a little bit annoying, but well, this is the way it is. Seen by especially the polar coordinate example. It's not entirely clear how come the geodesic equation will give us the straight line, as they're supposed to be. Right? So there's that. And let me just give perhaps a little bit of a hint of what we're going to do next. Okay, so just a bit of a heads up what we're doing. So next time we will be covering covariant differentiation, which is an application of the Christoffel symbol. So after that, after covariant differentiation, we will be seeing some more. Are we going to cover curvature next? Hopefully. No, actually, next one is geodesic coordinates. Geodesic coordinates. Okay, so that's next. Covariant differentiation, geodesic coordinates, and what's next? Actually, the next one will be curvature tensor. So we're 2 units away from the curvature tensor. Okay, and this series is called Towards Curvature. So we'll see. Okay, so hopefully we will. Yeah. I mean, there's no hopefully. We will finish this stuff, and that's just the basic theory. Of course, practice still is absolutely needed to master this material, and perhaps see some application in physics, and well, in information geometry. So that's it for today. Thank you guys very much for watching the stream, and I will see you next time. Bye. There's no stream tonight. There's 2 actually tomorrow. Tomorrow morning it's going to be on PDE. Tomorrow evening is going to be mathematical statistics and ballistics. Anyway, I will see you guys next time.